The last big thing we have to talk about in IB particle physics are these things called Feynman diagrams. Now, I will preface this by saying Feynman diagrams are not an easy thing to do. We're going to go through some examples. The examples are not something we would expect you to know how to do immediately. I will show you what you would realistically expect to see on an IB exam. So we're going to kind of approach this from a different way. Feynman diagrams, in my experience, Feynman diagrams is not something I saw until a fourth year particle physics course. So the fact we're getting you to do a much more simplified version of that in high school, that's quite a task to ask of you. But we are going to keep it simple. We're not going to do any math with this. And the whole purpose of the Feynman diagram, it's basically like an accounting mechanism in particle physics. We're doing a bit of bookkeeping. What we're trying to do with a Feynman diagram is we're trying to look at the interactions of particles, but we're also trying to keep track of the conservation laws that the particles must obey. So the Feynman diagram is a pictorial representation of the particles that are involved in the interactions. It's named after a very famous physicist from the United States, Richard Feynman. Very interesting character. Read up about him if you have time. So what we're going to be looking at is we're going to be looking at the interaction between particles. And the first thing that we want to highlight is that all the conservation laws we've talked about, like charge, baryon number, and such, they all have to be respected at this thing called the interaction vertex. So the interaction vertex, to really simplify it, it's basically where something is happening. And we're going to see a few different examples of the interaction vertex, and I'll show you exactly what's going on there. So with the Feynman diagram, there's a couple of conventions. So what we're going to say is we're going to say time increases as we move to the right. So time is going to be on the horizontal axis, and space, like physical space, is going to be represented on the vertical axis. We don't actually explicitly draw in the axes. These are just assumed, but you will see the odd case where the axes are drawn in. And on IB exams, sometimes they will switch. They'll say spaces on the vertical axis, or sorry, spaces on the horizontal axis and times on the vertical axis. Why they do that? Well, it's their business, not mine. But those are just things to be aware of, and I will highlight that again when we start to do some examples. Now, a line with an arrow in the direction of time. So if time is propagating in the rightwards direction, if we have a line with an arrow pointing to the right, this is going to represent a particle, like an electron, a proton, neutron. So we might have something like this. We might say that's an electron. If we have a line but the arrow is pointing against the flow of time, that is what we use for an antiparticle. So for example, if I want to draw a positron, I'll still draw my line, but I'm going to have the arrow pointing against time. So it's going to be pointing to the left. And this could be, our antiparticle of the electron, the positron. When we're doing Feynman diagrams, we also want to draw our exchange particles or our mediating particles. So when we talk about mediating particles, we're talking about the carriers of the fundamental forces. So we're only going to look at the three that are actually known to exist because we don't really know anything about gravitons. So photons, when we're sketching them in a Feynman diagram, it's just going to look a bit like a sinusoidal wave. That's going to be our pictorial representation for photons. For bosons, whether it's the W plus, the W minus, or the Z0, for the carrier of the weak nuclear force, we're just going to draw it as a dashed line. And then what type of boson we're using, we'll identify that. And then the gluons, the carrier of the strong nuclear force, kind of looks like a really messed up spring. So we kind of have something that looks a bit like this. Again, apologies for my poor drawings, but it is what it is. So just to finish out this video, we're going to start with a really simple case here. We're going to start with the case of the repulsive interaction between two electrons and a Feynman diagram. So we know from Coulomb's law in our study of electrostatics or electromagnetism that two electrons, because they're like charges, as they approach each other, they're going to repel. Now, because we're dealing with charged particles, we're dealing with the electromagnetic interaction. So our virtual particle, or our mediating particle in this context, is going to be the photon. So we're dealing with an electromagnetic interaction. Which means that we want to consider the photon in this interaction. Now, I'm just going to sketch it up here just to keep note. Again, we're going to use the vertical axis as space. We're going to use the horizontal axis as time. You don't actually have to sketch this. This is assumed. So what we want to have is we want to show the interaction. So there's kind of two parts to this interaction. There's before the interaction and there's after the interaction. So before the interaction, we're going to have two electrons coming towards each other. So I'm going to just draw two electrons approaching each other in space. So these are my two electrons that are approaching one another. Now, this is before the interaction, so before the electromagnetic force kicks in. So we have them both going towards the right because time is advancing on the right. We have them physically approaching each other in space. Now, what is happening according to particle physics? Why these electrons are being repulsed? What's going to happen is that one of these electrons, and it doesn't actually matter which one of these electrons is going to emit a photon. The one that emits the photon, again, it doesn't matter which one of them will emit a photon, the other's going to absorb that photon. So let's say, for example, this top electron here, let's say it emits the photon. So what we're going to do is we're going to sketch a photon being emitted. And we're going to draw that photon with our symbol for the Fineman diagram here, our pictorial representation of the photon. Now I'm just going to extend that electron a little bit more to when it gets that photon. So this is prior to the interaction. Now, what's happening after the fact? Once this electron emits this photon, it's going to start to move away from the other electron. So we're going to see it moving away in space since it's emitted a photon. And since this electron down here has now absorbed a photon, it's going to also move away from the other electron. So this is meant to be after the interaction. And then, of course, this is our photon, or our mediating particle. So what we have is we have two electrons coming in towards each other. This electron up top is going to emit a photon, the carrier of the electromagnetic force. When it emits a photon, it's going to start to move away. When this electron down here absorbs this photon, it's going to start to move away as well. So we have them approaching, and then we have them repelling due to the electromagnetic force. And then that electromagnetic force is carried by the photon. So this is a very common Feynman diagram that we see. This is kind of the most basic of the Feynman diagrams. We're going to look at a few more, but this is just to start you out.